Welcome to Spring LIB.
Okay, we have the following alkene. And we are reacting that with HCl. I'm going to draw this HCl with an explicit bond between the hydrogen and the chlorine so that I can step through the mechanism, because I think that's the simplest way to explain why we get the product that we get. Now recall that whenever you react a double bond with HX, the double bond will swing open and attack the hydrogen, whereas the electrons between the hydrogen and the chlorine will remain behind on the chlorine, or X in the case of a general HX. Now, when a double bond swings open and abstracts the hydrogen, as in this case, we can only put the hydrogen on one of the two carbons participating in the double bond, and the other carbon that did not get the hydrogen will end up with a positive charge and become a carbocation. Now, I'm going to draw both possible outcomes of this step. We will either get hydrogen on the innermost carbon and a carbocation on the terminal carbon, or we will get a carbocation on the secondary carbon and a hydrogen on the terminal carbon. Recall that there are other hydrogens on this molecule. I am only drawing this single one in to show that it's coming from this previous step. So be aware that there are in fact two additional hydrogens here, for example, and a single hydrogen here, and so on and so forth. Right? I'm only drawing in the ones to illustrate the point that we have just added it. Now, I would ask you, which of these two structures is more stable? We have a primary carbocation or a secondary carbocation. Remember, the more substituted the carbocation, the more stable it is. Therefore, the secondary carbocation would be the direction that this reaction would proceed. Now, from this step, we have to make one more consideration. Is there some hydrogen or methyl group that could migrate that would further stabilize our secondary carbocation? Notice that our secondary carbocation neighbors a tertiary carbon, and that this tertiary carbon bears a hydrogen, and whenever we have carbocations that are lower substitution than a neighboring carbon, we'll either see migration of a hydrogen or methyl group to shift the carbocation to the more stable position. In this case, this hydrogen will shift over to the secondary carbon, which in practice means that the hydrogen and the carbocation will effectively switch places. So the product of this so-called hydride migration the result of this hydride migration will be a hydride or a hydrogen here and a carbocation at this tertiary center. Finally, the Cl-, which we generated in the first step, can attack, generating the chloroalkane that we expect when adding HX across a double bond, like so.